In this video, we're going to talk about linear inequalities. So we've spent a lot of time talking about systems of equations, specifically linear equations. Now we're going to talk about what happens if you take that equal sign and you make it an inequality sign. So less than, greater than, less than or equal to, greater than or equal to. A lot of things we know about equations are going to carry through, but we're going to extend that. What happens if we change the equal sign to an inequality sign? Well, some things stay the same. What we know so far still holds, but additional things happen when we have an inequality sign. So what is a linear equation? Well, linear means when we graph it, it's going to graph as a line. So it could be a vertical line, it could be a horizontal line, or it could be a diagonal line. Doesn't matter. When we graph a line, though, what happens is that we divide our coordinate plane into two half planes. So keep in mind the coordinate plane is still infinite, so half is kind of relative. It's not like dividing something finite into two parts. We're dividing something infinite into two parts, but we're going to call them half planes. So depending on the type of line we have different kinds of half planes. That line that divides them is called the boundary line. So we have two different versions of this kind of problem. Say we have a linear equation, we graph it, we graph the line representing that equation. Say it's a vertical line. If we have a vertical line, that's going to be a vertical boundary line. It's going to divide our entire coordinate plane into a left half plane and a right half plane. Again, keep in mind these are both infinitely large. Neither is necessarily bigger or smaller than the other because they're both infinitely large. We just think of it as a left half and a right half. Now, if we graph the line and it's either horizontal or it's diagonal, then again, we divide into two half planes, but we're going to call it the upper half plane and the lower half plane. Again, they're both infinitely large, so depending on what portion of the coordinate plane we're looking at, it may look like one portion is larger, one portion is smaller, but that's not necessarily the case because again, the coordinate plane is infinite. It continues forever in all four directions. So half, smaller, larger, all of those terms are kind of relative. So we have our boundary line and the boundary line splits us into two separate parts. So given a linear equation, what results in the graph of a line, each of the half planes, so the left plane, the right plane, or the upper or lower half plane, is actually associated with a linear inequality. So if rather than just the line itself, which is represented by the equation, say we wanted to represent the entire side of the coordinate plane, the entire side of the coordinate plane actually results from a linear inequality, algebraically speaking. So if we wanted to graph something like that, the equation gives us a line and inequality gives us the coordinate plane side based on that particular line. Now the plane we get, the plane we shade, the left, the right, the upper, the lower, is going to depend on the inequality sign. So is it less than? Is it greater than? Is it less than or equal to? Greater than or equal to? Different inequality signs are going to result in us choosing or shading a different portion of the coordinate plane. So let's look at a really basic example and think about how all these parts work together. So we want to graph the line y is equal to x minus 2, and then also graph the linear inequalities that we would get if we took the equal sign and made it a greater than, and if we took the equal sign and made it a less than. And we want to put them all on the same coordinate plane. So we've talked about different ways you can graph a line. But one of the easiest ways to graph a line is just to look for intercepts. In other words, let your x be 0, solve for y. Let your y be 0 and solve for x. So say we let our x be 0. In other words, we're taking the x in this equation, replacing it with a 0. So we have 0 minus 2, which is going to give us negative 2. So when x is 0, y is going to be negative 2. So that's going to be one of the ordered pairs that solves this equation. So that's going to be one of the points on the line that we get. So 0, negative 2. That's going to be one of the points on the line. We can do the same thing if we let y be 0. So 0 is equal to x minus 2. If I add the 2 and move it over to isolate my x, then I get x is equal to 2. So when y is 0, x is equal to 2. 2, 0 is an ordered pair that solves this equation. So that point is also on our line. We could pick additional points if we want. For instance, if we let x be 1, we get 1 minus 2, which is negative 1. So y would be negative 1. So 1, negative 1 is also a point on this line. Notice if we connect the dots, connect the points, we could get infinitely many more in either direction, continuing forever and ever. Technically speaking, all we need are 2 points to graph the line, but we could get as many unique points as we wanted, just depending on what the goal is. So that's what results if we graph the actual equation. Now, if we take the equal sign and we convert it to an inequality sign, something different happens. So say we convert it to a greater than sign. What does that actually represent graphically speaking? Well, we can actually graph this the same way we graph the lines. So we graph the lines by picking an x value or picking a y value, solving for the other variable. That gave us some ordered pairs. We converted those to points and graphed them. Same kind of thing, but we actually have a lot more flexibility here. In terms of a line, x and y are related in a very specific way. In terms of an inequality, x and y, we have a little bit more flexibility. So say, for instance, we let x be 0. So we're letting x be 0. I'm going to plug in 0. So we have 0 minus 2, which is negative 2. We know that y has to be greater than negative 2. Not y has to be equal to, but y has to be greater than negative 2. The biggest difference here is now y is not a single fixed value. Y can be anything we want as long as it's greater than what we get when we plug in a 0 in place of x. So 0 minus 2 is negative 2. Y has to be greater than negative 2. So it could be negative 1, that's greater than negative 2. It could be 0, that's greater than negative 2. It could be 1, it could be 2, it can be anything we want. It doesn't have to be integers, it could be fractional values, doesn't matter. Y can be anything we want as long as it's greater than what results from that particular x value. So these 2 points are included in the graph of this inequality because they make that inequality true. Now, say we let x be 1. So 1 minus 2 gives us negative 1. So if x is 1, y has to be greater than negative 1. So it could be y equals 0, y could be 1, y could be 2, anything we want. So on and so forth. Say we picked x equals 2. Same idea. We're plugging in that value for x. Y just has to be greater than whatever results from that value of x. So we end up with several points that we could graph. What we're going to notice is that all of these points have one particular thing in common. So let's think about where these points are. So 0, negative 1 would be right here. 0, 0 would be right here. 1, 0, and 1, 1. Here's 1, 0. Here's 1, 1. 2, 1, and 2, 2 would be right here. What these points have in common is they're all on the same side of this line that we got by graphing the equation form of this relationship. All of them are in the upper half plane. And these are only a small sampling of the points we could get resulting from this inequality. What that tells us, though, is that this particular inequality gives us points in the upper half plane. So the graph of this inequality is actually the entire plane, entire half of the plane that's above this boundary line. All of these points that are above the boundary line are representative of this inequality. Now, if we change the greater than to a less than, probably exactly what you think is going to happen. Same idea. Say we pick some x values, plug in, get y values. That's going to give us a starting point for the graph. So say we let x be 0. So 0 minus 2 is going to be negative 2. If we want to graph this inequality, we need y values that are less than negative 2. So when x is 0, y just has to be less than negative 2. So it could be negative 3, it could be negative 4, negative 5, anything we want as long as it's less than negative 2. So if x is 0, we can have y values, anything we want as long as it's less than negative 2. Say we let x be 1. Well, 1 minus 2 is going to be negative 1. So y has to be less than negative 1. So it could be negative 2, negative 3, anything we want. Whenever x is 1, y just has to be less than negative 1. So 1, -2, 1, -3, anything we want, so on and so forth. That gives us another sampling of points representative of this particular inequality. And again, all these points have something very specific in common. If we were to graph these points, think about what those look like. So 0, -3 would be right here. 0, -4 would be right here. 1, -2, 1, -3, well, 2, -1, 2, -2. All of these points are below our boundary line. So this particular inequality is representative of the half plane that's below our boundary line. So what we now have is essentially the whole coordinate plane that's been separated into distinct regions. So the equation form of this relationship results in the actual line. We call that the boundary line. It's the line that's splitting that coordinate plane into pieces. If we're taking the relationship and we want to look at y such that it's greater than x minus 2, that represents all the points above our boundary line. And if we want to change the relationship such that y has to be less than x minus 2, that's going to be representative of all the points that are below the boundary line. So when we say we want to graph a linear inequality, the graph of the linear inequality is going to include the boundary. In other words, where do we cut off? Where does one side of the coordinate plane separate from the other, as well as the shading that we want. So if our goal was to graph this greater than inequality, our graph would include that boundary that's separating the two parts of the coordinate plane and that portion of the coordinate plane that we actually shade based on the individual ordered pairs that we can get that satisfy this inequality. So let's generalize graphing a little bit more, and then we'll look at some examples. So in general, we've got a linear inequality, any inequality we want. Number one, we're going to start by graphing the boundary line. What does that mean? Well, what it means is we're going to take that inequality and just for a moment, we're going to pretend that it's not an inequality. We're going to pretend that it's an equation. We want to graph the line that would go with that equation, that would go with that inequality. So take away the inequality sign, pretend that it's an equal sign for a minute, graph the equation form of that inequality. That's going to give us a boundary line. Now, how we graph the boundary line is going to be dependent on the situation we're in. So anytime our inequality is a less than or a greater than, in other words, it doesn't have the equal to part, we're actually going to graph as a dotted line. We'll talk about why that is in just a second. Now, if our inequality sign has the equal to part, in other words, it's a less than or equal to or a greater than or equal to, we're going to graph as a solid line. So dotted if there's no equal to, solid if there is an equal to. So as you can tell at this point, because we're graphing lines, you may want to have a ruler, some type of straight edge with you. That's going to help you with your graphing. Okay, now we know that's not the whole story. An inequality is representative of an entire region. It's got the line, the boundary, but it's an entire region based on where that boundary is. So we're not entirely done. We're halfway there. What we need to know, though, is which region represents our particular inequality. Is it the one that's above, the one that's below, one that's left, one that's right? We don't officially know yet. All we need to do, though, is we need to know what happens for a single x value. So what we're going to do is we're going to choose a test point, some point somewhere in the coordinate plane, any point we want except a point that's on the boundary line. So it doesn't matter what point we pick, it just has to be a point that's not on the boundary line. And we're going to take that point and we're going to plug it into the inequality. So plug in the x value, plug in the y value, and then see what happens. So I've made a note, if possible, you want to pick 0, 0. Now that only works if 0, 0 is not on your boundary line. But if it's not on your boundary line, then that's the point you want to choose. Why is that going to be beneficial? Well, we're taking individual values and we're plugging them in place of our variables. Plugging in 0, 0 usually results in something that's easy to simplify. So you're less likely to make a mistake, algebraically speaking, if you pick easy numbers to plug in. Again, it doesn't change your answer choosing something else, but 0, 0 typically results in something that's easy to simplify. So if possible, ideally we want to pick that just to make our lives a little bit easier. What's going to happen once we plug in the values in our test point is we're either going to get an inequality that is true or we're going to get an inequality that is false. If we get an inequality that's true when we plug in our test point, when we plug in the values in our point, then we know that that particular point is part of our solution, that it's part of the region we want. So what that tells us is we're going to shade the side of the boundary line that contains that particular point, because that point is something that we want to be included as part of our solution. Now, alternatively, if we plug in our test point and we end up with an inequality that is false, we're going to shade the other side. What the inequality then tells us is that point we chose is not part of our solution. So we want to shade the side of the boundary line that doesn't have that particular point. So let's look at a few examples. So here's our first inequality. 2x minus 3y is less than or equal to 6. Okay, so this represents a half plane in the coordinate plane separated by the boundary line that we would get if we treated this inequality as an equation. So I'm going to treat it as an equation for just a minute. In other words, I'm going to take the inequality sign, I'm going to make it an equal sign. I know this graphs as a line. So you can go about graphing this in a couple different ways. I went and isolated the y, so you could graph from slope-intercept form if you're familiar with that. Otherwise, you can graph using your intercepts as usual. So if you let x be 0, this term goes away, which would mean y would have to be -2 in order to make that true. So 0, -2 would be our y-intercept. If we let y be 0, then this term goes away. That means x would have to be 3. So 3, 0 would be our x-intercept. Once we have those 2 points, we can connect the dots. We have our line. Now, how we graph that line depends on the type of inequality sign we have. So we have a less than or equal to. That equal to part tells me I want to graph as a solid line. Why do I want to graph as a solid line? Well, solid line tells me that the actual line itself is part of my solution. The less than part represents one of the half planes. The equal to part represents the actual line, what we actually just graphed. By saying that the equal to part is part of my inequality and part of my solution, I know that the line itself is one part of my solution. So my solution contains the line and it contains the half plane we get when we shade one side of the line. If I didn't have that equal to, like in the second example, that means that the line gives us a boundary, but because the equal to is not part of the inequality, it's not actually part of the solution. So we have a boundary, but we don't want to include the boundary as an actual part of the solution, so we graph it as a dotted line. So dotted line means it's there, but not really. Solid line means it's there, and we are considering it to be part of the solution. So in this case, once I graph that line, find those ordered pairs, graph my intercepts, I want the line to be solid because it's part of my solution. Okay, so we have the boundary line. Now we need to determine which direction would we shade. So are we shading everything above it? Are we shading everything below it? I'm going to base that on a test point. So here's my line. I can pick any other point in the coordinate plane as long as it's not on that line. So notice 0, 0, the origin is not on that line. So I'm going to pick 0, 0 as my test point. What I want to know at that moment is if I were to plug in x equals 0 and y equals 0 to my inequality, what happens? Do I end up with something that's true? Do I end up with something that's false? So I'm going to plug in 0 for x, I'm going to plug in 0 for y, and then I want to simplify the resulting inequality. So this is what I'm doing algebraically. So 2 times 0 is 0, 3 times 0 is 0, 0 minus 0 is just 0. So what this results in is 0 is less than or equal to 6. That is a true statement. 0 is less than or equal to 6. So what that tells me is 0, 0 makes my inequality true. So it's one of the ordered pairs and one of the points that's part of my graph. So if I look at where my test point is, I took my test point, I used it, and I ended up with an inequality that's actually true. I'm going to shade the side of my boundary line that does contain my test point. My test point is part of my solution, so I'm going to shade the side that does contain it. As it turns out, if you picked any other point in that region, you would have ended up with the same result. You would have ended up with an inequality that's true. Say instead you picked, I don't know, 2, -2, which would be on the other side of the boundary line. If you were to plug in 2, -2 to this inequality, you would end up with something that's false, which means that particular point you chose is not part of the solution. That would result in you shading the other side of the coordinate plane. So since our test point worked, we're going to shade the side of the coordinate plane that has that particular point as a part of it. So our solution in this case is going to be the upper half plane. Let's look at another example. So y is greater than -3. I'm going to start with the equation that comes from this. I need to know where is my boundary. So the boundary is going to be the line that results from this inequality. In other words, take the greater than, make it an equal to. So our line is y is equal to -3. Now this is a special case because we don't have an x, we just have a y. So this represents all the ordered pairs that have a y coordinate of -3. What this means is that x and y are independent of one another. X doesn't have any impact on what y is, and vice versa. Y has to always be -3. So I could have 0, -3, 1, -3, 2, -3, -1, -3, -2, -3, so on and so forth. Any ordered pair that I want, as long as the y coordinate in that ordered pair is -3. What that results in is actually a horizontal line. So it's the horizontal line that goes through, not surprisingly, y is -3. So it has a y-intercept of -3, and notice it doesn't actually cross the x-axis. Now this boundary line is graphed as a dotted line because we don't have an equal to as part of our inequality sign. What this means is that this is a boundary, but it's not part of the actual solution. So it differentiates solution from non-solution, but the line itself, the boundary itself, is not part of the solution. So we graph it as a dotted line. Now we need to determine, do we want the portion of the coordinate plane above it, or do we want the portion of the coordinate plane that's below our boundary line? So I pick my test point. Again, 0, 0 is a good option because it's not on the line and it's going to be easy to plug in. So my test point is 0, 0. I'm going to plug it into my inequality. Now notice again, my inequality only has a y, so I can't plug in x equals 0. All I can plug in is y is equal to 0. So I'm going to plug in my 0 for y, which gives me the inequality 0 is greater than -3. That is actually a true statement, algebraically speaking, which means that this particular test point is part of my solution. So I want to shade the region in the coordinate plane on one side of the boundary line that does contain this point. So this point was above our boundary line. This point is part of the solution. So I want to shade the region that does contain that particular point. So our graph for this inequality is going to be the portion of the coordinate plane above the boundary line at y equals -3, but not including the actual boundary line. Okay, let's look at another. So 2x is greater than or equal to 8. Okay, first thing I want to do, I want to graph the line. So take away your greater than or equal to, make it an equal to, pretend it's a line for just a minute, graph the boundary. I'm going to start by isolating the x, which will make this a little bit easier to graph. So I'm going to divide that 2 from both sides so we get x is equal to 4. This is another special case like the one before. Notice now we have an x, but we don't have a y. So this line consists of all the ordered pairs that have an x coordinate of 4, regardless of what the y coordinate is. So we could have 4, 0, 4, 1, 4, 2, 4, 3, so on and so forth. Any point we want as long as the x coordinate is 4. That results in a vertical line. So it's the, again, not surprisingly, the vertical line that goes through x is equal to 4. This one doesn't have a y-intercept. It only has an x-intercept. Now we know to graph this as a solid line because our inequality sign is greater than or equal to. That equal to part tells me that it's going to be a solid line. It tells me that not only is this the boundary that separates one side of the coordinate plane from the other, but the boundary itself is part of my solution. So the greater than portion corresponds to a half plane. The equal to portion corresponds to the boundary line that we do want as part of our solution. Again, I'm going to pick my test point. 0, 0 is a good option because it's not on the line. I'm going to plug in my 0. Here I can only plug it in for x. So in other words, y doesn't actually matter, just the x value. So I'm going to plug in x equals 0. So that gives me 2 times 0, and then greater than or equal to 8. So 2 times 0 is going to be 0. So we have the statement that 0 is greater than or equal to 8. Well, that's actually a false statement. Algebraically, that is considered to be false. So what that tells me is that this test point is not part of my solution. 0, 0 is not part of my solution. So the side of the coordinate plane that contained this test point is not the side we want to shade. We want to shade the side of our boundary line that does not contain this point, because this point gave us something that was algebraically false. So that means we're going to shade the right-hand side of the coordinate plane, everything that's to the right of our boundary line. Okay, let's look at another example, and then we'll look at an application. X is less than 3y. Okay, so again, we can graph this using intercepts if we want, or we can graph using slope-intercept form, again, if that's something you're familiar with. All you need is 2 ordered pairs. So the line would be x is equal to 3y. Say we let x be 0. Well, if x is 0, then y has to be 0 as well in order to make this true. Why does that work? Well, say x is 0 and you want to isolate y. Just divide out your 3. 0 divided by 3 is still 0. So 0, 0 is on this line. Now, 0, 0 is both an x-intercept and a y-intercept, which means if you try to find the y-intercept, you're not going to get any new ordered pair. X-intercept, y-intercept, they're the same. That means we need to find another point, something that's not an intercept, in order to be able to graph this. If, for instance, I were to let x be 3, so if I were to plug in x equals 3, we have 3 is equal to 3y. Well, if that's the case, then y has to be 1 in order to make that true. So another ordered pair, another point that's on this line would be the point 3, 1. So I can plot that as well. I have 2 points, which is enough to uniquely graph a line. I know this line has to be a dotted line because I don't have an equal to as part of my inequality. So I'm going to graph that dotted line. That's going to be my boundary line. The question then is, do I want everything above it, or do I want everything below it? Now, we can't use the test point 0, 0 this time because it's actually on the line. We have to choose a point other than something on the line. What we choose, again, is not a big deal. You can choose anything you want as long as it's not on the line. Don't choose something that's close to the line, though, because if your graphing is not super accurate, you may end up choosing something that's actually on the line that doesn't look like it is, but again, that's dependent on how well you graph. So choose a point that's very clearly not on the line. So in this case, I chose the point 0, 2, which is very clearly not on this line. It's above the point 0, 0. What I want to know is what happens if I plug in 0, 2 to my inequality. Do I get something that's true, or do I get something that's false? So I'm going to plug in x equals 0. I'm going to plug in y is equal to 2. So we end up with 0 on the left-hand side. We plug in a 2 on the right-hand side, so we get a 6. So I have the inequality 0 is less than 6, which is a true statement. So that tells me 0, 2 is one solution to my inequality. It's part of the whole solution. So I'm going to shade the half plane that contains that particular test point. In this case, the test point was above my boundary line. So I'm going to shade the half plane that's above my boundary line. Okay, so let's look at an example of how we might use something like this. How does a linear inequality come into play? How might we use something like this to model a situation? Well, here's our setup. So a concert promoter wants to book a band for a stadium concert. A ticket for admission to the playing field will cost $125, and a ticket for a seat in the stands will cost $175. Now, the band wants to be guaranteed total ticket sales of at least $700,000. I want you paid attention to that phrasing, at least. Not exactly 700,000, but at least. So 700,000 would be okay. So at 750, so at 800, we just have to make at minimum $700,000 in sales. So our question is, how many tickets of each type must be sold to satisfy the group's requirement? So we want to express the answer as a linear inequality and draw its graph. Now, how do we know this situation is representative of an inequality? This is pretty similar to problems we've solved before in the sense of somehow individual parts contributing towards a total. We've looked at what sales type situations look like. The reason this is an inequality rather than something indicative of an equation is that phrasing, at least. At least means we have more than one possible outcome that would be satisfactory. It just has to be some outcome that results in total sales of 700,000 at minimum. So again, 700, 710, 720, 730, anything like that would be fine. Different amounts of ticket sales would result in that particular kind of total. We just need a total that covers the 700,000 and possibly surpasses it. So any situation where we have something unknown, we need to start by labeling our variables. So our question is, how many tickets of each type must we sell? So we have two types of tickets. So we have tickets on the playing field. We have tickets in the stands. So playing field tickets cost $125. Stands tickets cost $175. So I'm going to let those two be my variables. So X, we're going to call X the number of tickets on the field, and then Y is going to be the number of tickets in the stands. So those are the values we're interested in at the moment. Now, anytime we want to represent something related to sales, remember it's going to be how much we sell multiplied by how much we sell it for. That's representative of our revenue. So if we sell, for instance, one ticket on the field, we would make $125. If we sold two tickets on the field, we would make $250. If we sold three, we'd make $375, so on and so forth. So if we multiply the number of field tickets by how much we're selling them for, in other words, take X and multiply it by 125, then that's the portion of sales that we get from sales on the field. Okay, now same thing for tickets in the stands. So if we sell one, we make $175. If we sell two, we make double that. If we sell three, we make triple that. So if we multiply the price by the number of tickets we sell for the stands, that's going to be that portion of the total amount of sales. So if we add those two components of sales together, then what we know is somehow that has to be related to the total in question, which is 700,000. But it doesn't necessarily have to be equal to 700,000. It could be, that's allowed. At least means 700,000 would be okay, but certainly selling more than that would be okay as well. That tells us that the correct inequality sign has to be greater than or equal to. So the equal to part is allowing the total sales to be exactly 700,000. The greater than part tells us as long as we pass the 700,000, then that would be fine as well. So 125x plus 175y is greater than or equal to 700,000. That is the inequality representing our sales in this situation. Now, we can reduce that a little bit. So we have a common factor of 25 among all those numbers. So I could take 25 and I can divide it out from the left-hand side of the inequality, the right-hand side of the inequality, and I can reduce it and I can make it a little bit more manageable. So another version of our inequality, the simplified version, in some ways the preferable version, would be this particular version. So 5x plus 7y is greater than or equal to 28,000. So this is the inequality representing our sales in order to satisfy this requirement that we make at least 700,000. Now we want to graph that. We have to keep in mind that 700,000 can be reached in different ways. We can sell different combinations of field tickets and stand tickets. And again, if we pass the $700,000 limit, then we're also potentially selling different numbers of each type of ticket. So we want to model all the different combos that are available by graphing this linear inequality. So I want to start with the line. In other words, take that inequality sign, take it away, make it an equal sign, and then graph the line that goes with that. Now, because we have such big numbers, again, we can graph using intercepts, but the intercepts represent big numbers as well. So one good option in this case is, in order to graph, maybe we want to use a different scale other than just counting by one. So in this case, if we find our intercepts, if we let y be 0, we determine that x has to be 5,600. If we let x be 0, we determine that y has to be 4,000. So because both of these numbers are in the thousands, potentially we could count by 1,000 instead of counting by 1. Now, that means for our x-intercept, we're going to have to mark something that's between grid lines. That's okay. That's not a big deal. These kind of graphs are a little bit more general. We're not as interested in really specific detail in terms of graphing. This is just a generally representative picture of the situation. So if I count by thousands along the x-axis and along the y-axis, then this will be pretty manageable to graph. So I'm going to graph my intercepts, connect my dots. I know this line is going to be a solid line, again, because if I look at my inequality, the equal to is part of the inequality. So I'm going to graph that line as a solid line, which tells me that the boundary is going to be part of my solution. So every ordered pair on that boundary is a possible solution to my inequality. Okay, now we need a test point. We need to determine which part of this are we going to shade. I'm going to pick 0, 0, again, because that's not on the line. It's easy to plug in. So I'm plugging in 0, 0 to my inequality. That means the left-hand side of the inequality comes out to 0. So I have 0 is greater than or equal to 28,000. Well, we definitely know that's false. So that means I identify where my test point is, and I'm going to shade the other side of the boundary line. Now notice I didn't actually shade everything above that boundary line. I left some key areas out. What you'll notice about what I shaded is that I only shaded within the first quadrant. Well, why is that? Well, we have to think about what it means when we're in a real world situation. We have some limitations on actual values that x and y can take on. We can't sell a negative number of tickets, so our variables represent the number of tickets we're selling. We can't sell -5 tickets. Something like that doesn't actually make sense. We can only sell positive numbers of tickets, which means x has to be a positive number and y has to be a positive number as well. Minimum, we can sell 0 tickets, but we can't sell negative tickets. What that does to our graph is it limits it to the first quadrant. So we're using the boundary line to separate one half plane from the other, but we have to further impose restrictions on x and y because we're in the context of a real situation. So because we can't sell a negative number of tickets, we're shading a half plane, but we're restricting that half plane to just the portion that's in the first quadrant of the coordinate plane. So that particular upper half plane, but the portion of the upper half plane that's confined to the first quadrant, represents our actual solution. So any combination of values in there represents a possible solution. Now, technically, if we're going to be a little bit more exact, we also have to keep in mind that you can't sell a fractional number of tickets, so you can't sell half a ticket. So technically speaking, our solution would be all ordered pairs in that region that represent integer solutions. So 1 of one type, 2 of another type. You can't sell 1/2 of one type and 3/2 of another type. Something like that doesn't make sense. But we're going to leave that whole region graphed just for simplicity in this case. So keep in mind, interpreting your solution, you may have to think in a little bit more detail based on what's really going on. But in general, our graph is representative of the situation at hand.